in the Lewis dot lab, which we sometimes call the molecular geometry lab, you will need to be able to draw Lewis dot structures and answer questions about them. And so let's just start with this one. We have A and B, and I'm going to do some calculating up here. It's AB2, and then A and B both have 6 valence electrons. And so if I want to count the number of valence electrons, it would be 6 plus 2 times 6. And in other words, I've got 18 valence electrons. And then to start my Lewis dot structure, I always put the one that's different in the middle. So A, there's one A and 2 B's. Start with single bonds. I'm going to start putting on these electrons. Remember that a bond counts as 2. So I already have 4 on there. I'm going to start by putting them on the outside atoms first, or the surrounding atoms, and then look at how many I have. I've only put 16 on there, 2, 4, 6, 8, and then 8 here. So if I have leftover ones, which I do, I have 2 leftover electrons. They go on the central atom. Okay, after I've got all my electrons on, I check to see if I have octets on everything, and I should on the outside ones, but the inside one I need to check, and this one only has 6. It has 2, 4, 6, and it needs 8. So to get 8, what I'm going to do is move 2 electrons in. I'll move these and make a double bond like that. Okay, and now I can tell that A has 4, 6, 8. It's 8. But when I made that double bond, you can tell I had to make a decision. I had to decide which side to make the double bond. So I need to draw both ways. Okay, and I draw both ways, and in this case, that means I have resonance. And I would say I have 2 resonance structures. We put arrows between them. And what's really happening here, let me draw my second one pink, is that those 2 electrons represented by the pink, they're not really on the right or the left. They're being shared by the whole thing. So the true structure is somewhere in between those 2 resonance structures. Okay, so let's go through some of these answers on here. I have how many lone pairs on A? A lone pair is this. And so I have 1 lone pair. How many electron groups? This is around the central atom. And so what I'm doing when I'm counting electron groups is I'm counting a bond counts as a group. Doesn't matter if it's double or single or triple. And then a lone pair counts as a group. So that's 3 electron groups. We won't ask you about the number of groups, electron groups on the test, but most instructors look at that first before we go to electron geometry. For the electron geometry for 3 electron groups, the electron geometry is trigonal, planar, and then on this, the molecular geometry, so here's the electron geometry. The molecular geometry only looks at where the atoms are. So I have, and the lone pair that's here does not contribute to the molecular geometry. So the molecular geometry is bent, and the angle is 120. Is it polar? And I would say yes, this is polar. Because it's not balanced. It has a lone pair on one side. So you can think about it as having electrons out here that make it this end more negative. The only way having lone pairs would not cause it to be polar is if there was some on the exact opposite side. So if you had a linear molecule somehow. But anyway, so let me see if we answered all of these questions. I guess we did. Let's look at our geometries and polarity real quick. So this is kind of extra. So what is a nonpolar bond? A nonpolar bond is anytime you have the same element bonded to itself. In other words, both atoms are the same element. That will be nonpolar. Or the other kind of exception we give you, a very common bond is carbon to hydrogen. That is also nonpolar. Polar bonds are basically, we're going to just assume anything else that's a covalent bond where you have different elements. It's going to be somewhat polar. And that's a bit of a simplification, but that'll work for general chemistry. Okay, let's look at our geometries. And actually, I did not draw the 2 atom ones on here. Okay, so this one, because there's different elements, as long as it's not CNH, this would be polar, and this would be non because it has the same element. Another kind of linear one would be where you have like this, and this would be non, because even though it has polar bonds, you see how they're opposite each other, they kind of balance each other out. So that would be a non. It wouldn't have a positive end and a negative end. Let's look at these other geometries. This is the electron geometry. These all have electron geometry of trigonal planar. This one's geometry, molecular geometry, is trigonal planar. This one's electron geometry is, or molecular geometry is bent, and this one is linear. And then for polarity, what you have to look for is balance. And these 3 atoms are the same type. If any of those was a different element, this would be polar. But this is nonpolar. Again, a lone pair throws things off because it literally is 2 electrons that are out here on this side. So this would be polar. We're looking at, does the molecule have a negative end and a positive end? And this is definitely, lone pairs create a negative end. So this would be polar as well. Okay, I'm going to put a little line here. So the electron geometry on all of these is tetrahedral. And on the lab exam, we only go up through this geometry. We won't do the trigonal bipyramidal and the octahedral. Okay, so electron geometry is tetrahedral. The molecular geometry on these, this is tetrahedral. This one is trigonal, pyramidal. This one is bent, and this one is linear. And then let's look at the polarity. When there's no lone pairs, as long as all of these elements are the same, then it will be nonpolar. If one of those elements were different, it would be polar. With a lone pair again, that creates a negative end of the molecule, so this is polar. Again, negative, very negative lone pairs on this end. This is polar. And then when it's linear, if it's 2 different elements, unless it is carbon and hydrogen, it will be polar. Okay, so that's kind of how you assess our main shapes and polarity. Our X has 5, our Y has 7. And so to get the number of valence electrons, I would say 5 plus 7 times 4, or 4 times 7. And then for the positive charge, that means that it's lost an electron. Remember, electrons are negative, so I'm going to subtract 1. And that gives me 32 valence electrons. When I'm going to start my structure with my different one in the middle, I'll start with all single bonds. Then I'm going to start putting these electrons, always put on the outside first. And once I get all of my outside atoms with their octet, I count. And I have 32 electrons on there, so I don't have any to put on the center. Never make a double bond unless you need one. Notice X already has 8, so don't make a double bond unless you have a shortage on that central atom, and we don't. Okay, and on this we also need to put brackets and a charge to show that overall it has a charge. Let's go through our questions over here. Number of electron groups. Again, what we're doing is we're counting around our central atom. A bond counts as one group, a lone pair is a group. So there are 4. So that makes the electron geometry tetrahedral. And that makes the molecular geometry tetrahedral. Is it polar? No, it's non-polar. Does it have resonance or isomers? It has neither. Okay, and just to show you this structure, it's our little pyramid. And all of the atoms, surrounding atoms, are the same type. So it is non-polar. On this one, I have 2 times 4 plus 2 plus 14. That's 24 valence electrons. I'm going to start by, when you have carbons, start by putting the carbons bonded to each other, and then whatever you have left, just distribute. Let's do one structure before we start considering other possibilities. Once I get all of my atoms on there, I put the electrons on the outside. Atoms. Hydrogen doesn't need any more. These already have 2. I've got all of my electrons on. And my carbons, though, I don't have them all on. I need 2 more. Then I check and I see that my carbons only have, well, this carbon only has 6. So I need to take that lone pair and put it here. And that will give me a double bond there. And now both of my carbons have enough. So now that I see what the basic shape is going to be, let's go ahead and figure out the first parts. How many electron groups? I have 1, 2, 3. And by the way, when we do this, you can choose either carbon because we're going to give you molecules where the carbons will have the same answers on these. So the electron geometry is trigonal planar. There are atoms on all 3 of those positions, so the molecular geometry is trigonal planar. And let's stop there and draw this the correct shape. So I have a double bond in the middle. And then these carbons are both trigonal planar. So I'll put them like this. Okay, and now that we see the shape, we know that there are other ways to connect this. So let's draw the other possibilities. In other words, we could have put both X's on the same one. Or we could have put, showed both X's pointing down. We could put one up and one down. Okay, so all three of our answers, and I'm done with this one. That was just starting out. All three of the answers so far are the same for these, but when we get to polarity, we need to assess each one. First of all, are these isomers or resonance structures? These are isomers. We have 3 different isomers. When you have different isomers, the polarities can be different on each one. So what we're looking at is treating these like polar bonds. Remember that the C to H is nonpolar, C to C is nonpolar, and so these are the only polar bonds, and if they're pointing the same direction, then that's going to make it polar. Same on this one, they're both pointing off to the right, sort of overall, so this is polar. But on this one, we have one pointing each way, they're opposite, so this one's nonpolar. Okay, so be sure to be able to distinguish isomers and resonance structures. We don't put arrows between isomers. They can each have their own polarity, and they're actually different compounds. They're made by connecting the atoms in a different order. Resonance structures, on the other hand, are where you can put the double bond in different places. They are not different compounds. They are just 2 drawings of the same one, where the true structure is somewhere in between. Resonance structures involve what we call delocalized electrons. Delocalized electrons were where we were saying that the double bond can either be on one side or the other. Those 2 electrons are shared by all 3. And that's it for our last experiment.